I've been thinking about how to go about doing the last chapter in my theoretical mechanics class this semester. This is a high-level undergraduate course in physics that revisits sort of Newton's law stuff, but with more math. And the last chapter that we're planning to cover is all about resonance in normal modes. And this is the quintessential example. You've got a couple of masses connected with three springs, and these are sort of solid walls here, so they can't move. And you're wondering, if you were to get this thing shaking along, like grab one, move it, and shake it along, is there any way that you get it so that both masses would move at the same frequency? And we're trying to figure out exactly, whether that's possible. And so the typical math, I'll walk through at least some of it here. The typical math one does, I'm going to do the absolute simplest model I can think of. All three springs are the same, the two masses are the same, and in fact all the three springs are the same exact length, and they're right now unextended. They're at their happy length. So if x were to move a little bit, or x1 or x2 were to move, what force would x1 feel? Well, if it stretches this spring a little bit, it'll be pulled back by that spring. The two coordinates conspire together to either stretch or compress this spring, and since that spring is also connected to that mass, it'll feel an additional force. A similar analysis can be made for the second mass. So here are our equations of motion. And what we're going to do is we assume that both particles move with some amplitude at the same exact frequency. I'm using complex notation here so that I can hit both cosines and sines at the same time. Ran out of room here a little bit. The notion is, okay, I'm going to plug these assumptions into my equations of motion, and I get a bunch of ugly, gross stuff, and some of it's cut off. But the point is, every single term has an e to the I omega t in it, so we're going to cancel every single one of those. So we'll cancel them all, because, of course, that can never be zero, so we're allowed to do that. The other thing I'm going to recognize right away is I only have two equations. I have three unknowns right now, right? What are the frequencies, and what's A and what's B? I can't possibly solve all three of those, so I'm going to quickly divide through by B so that what I'll actually solve for is A over B and the omegas, and I slipped in my masses here. So when I do that, my two equations simplify greatly to these two equations, and it relates to equations and two unknowns. The two unknowns are the ratio of A to B and omega. Well, that's two equations, two unknowns. It's not that hard to solve. You get these solutions. A is either equal to B or they're opposite. So in the movie, if you were to actually move this, they either both move together to the right and left together, which means this spring never gets compressed, or they move oppositely. So when this one moves right, this one moves left. And in fact, that second one we expect to be a higher frequency because then this spring gets involved. There's higher forces involved. It ends up being a higher frequency, and sure enough, you get about, well, this is frequency squared, but anyways, there's this extra factor of 3 involved. Now, that's a simple system, and most chapters that cover this stuff are going to do that. But typically, you rewrite the thing in matrix formulation, and you say, oh my goodness, we can just diagonalize this matrix. In fact, even the masses become a matrix. It gets nasty really fast, but this is the only way mathematically, analytically, that you can handle this stuff as the system gets more and more complicated. What I don't like is how this system in particular was already at the equilibrium location. What if you don't even know what the equilibrium location is? So before I get into how I'm thinking of doing it, let me show you some examples of what's happening here. So if you excite the system at the low frequency, you see how they both end up moving together, and the middle spring doesn't stretch hardly at all. If you excite at the higher frequency, you get this motion where they're moving equal and opposite. Okay, it's a much higher frequency. And if you excite at the wrong frequency, essentially nothing much gets going. What I want to do, the thing that I'm thinking about doing, is simply putting the equations of motion into Mathematica and having Mathematica solve the system. And in fact, go ahead and put some friction in here too so that we can figure out where they sort of land, so that we can have Mathematica find the equilibriums for us. And then if we move tiny little distances compared to those equilibria, hopefully we can figure out what frequencies the systems exhibit, and we're actually doing a direct measurement of the resonant frequencies. So that's what I'm thinking about doing in this particular chapter.